well, look, thanks. Okay, so thanks for coming. I know it's awful, some of these things we have to talk about, think about. So we should use the time efficiently. We got to talk about moments of inertia last time. That's the last topic. So I don't mind starting with questions on that, if you have questions on that, or anything else, because I think we can use our time for anything that you want to talk about that we've been doing. I'm sorry, which question are you talking about? I need a specific question. Well, no, we need to use our time efficiently, so let's talk about specific questions that you may have.
Will you be using the same problems from the test from previous tests on the final one, or will it be the same questions with new numbers, or will you be giving us just?
Well, no, they probably won't be the same questions per se, but there's similar topics. I mean, the topics are likely to be the same, but it certainly won't be the same questions as such. Let me just start with an example about moments of inertia. So since that's the last thing that we did, so here's a problem which might be helpful to consider. I'm going to have several objects here that all have the same mass. So in the first track, I'm going to put a hoop. You see there's a hoop right there in the first track. In the second track, I'm going to put a disc. In the third track, a hollow sphere. In the fourth track, a solid sphere. And in the fifth track, an ice cube. And they all have the same mass. And the objects, apart from the ice cube, they all have the same radius. Which do you think will win the race? So there's several things to consider about here. They're all going to roll down the slope. I've said that they all have the same mass. See, they all have the mass of 1 kilogram, a radius of 5 centimeters, and they all have mass m, mass m, mass m, mass n, the same radius r. Which object do you think will win the race? And why do you think, what are we trying to consider here?
Is this a frictionless surface?
Yes, I believe frictionless, yes. So what are we talking about here? Conservation of energy. So if they're going to start to roll down from rest, so what is the kinetic energy that they have at the top of the slope? So let's consider one object, for example, this hoop. They have no kinetic energy, so I'm going to say initial kinetic energy plus initial potential energy has to equal final kinetic energy plus final potential energy. So they have no kinetic energy at the top. What's the potential energy that they have? It's going to be mgh. Now they give us a height, I'll just call it h. So if we assume that this height is h, then the height of the object relative to the ground is h. So the potential energy would be mgh. Now when they get to the end of the slope, so if I consider, for example, the hoop, it's going to be moving, right? It's going to have kinetic energy. How much kinetic energy will it have at the end of the slope? It's definitely going to have 1/2 mv squared. But then we talked about last time, there's also what we call rotational kinetic energy. So not only does it have linear kinetic energy, 1/2 mv squared, but because it's going to roll, it will also have rotational kinetic energy. What is the formula that we learned for rotational kinetic energy? 1/2 I omega squared. So that's what we learned for rotational kinetic energy. Because an object that's rolling has got rotational kinetic energy. So should we just make a note that this is rotational kinetic energy, and this is linear kinetic energy. We should also consider the potential energy. How much potential energy do the objects have when they get to the end of the slope? I'm going to call it 0 because we can define it to be anything we want, but I'm going to call it 0 so that we'll call the potential energy at the top mgh. So the object rolls to the end of the slope. Now this is similar problems that we've done before, but what's new in this problem, compared to what we've done before, is this 1/2 I omega squared. So all the potential energy, MGH, will go not only into kinetic energy, which we've discussed before, because we've considered all masses to be point masses before this last section, but now we're talking about objects that roll. So of course the question is going to be, well, what is the moment of inertia? And the moment of inertia varies. And this is something that you look up. I think I have it in the. So I've got moments of inertia for various bodies available here. So, for example, a hoop. You can think of a hoop as being somewhat like a hollow cylinder, the thin-walled hollow cylinder. See, the moment of inertia is mr squared, whereas a solid cylinder is 1/2 mr squared. So we discussed last time that these are mathematical calculations that we make in calculus, so you don't have to worry about how they're derived, you just look them up. So when you're doing the homework, you would look them up. So a hoop has a moment of inertia of mr squared. A cylinder has a moment of inertia of 1/2 mr squared. What's a solid sphere? 2/5 mr squared. A hollow sphere, hollow, that means it's all the masses around the circumference, around the surface, 2/3 mr squared. These are not numbers that you need to be able to derive, so you look these up in a book. And the principle is that the more mass that's concentrated around the surface, the greater the moment of inertia. Because it's more difficult to turn something where the mass is far away from the center. So the more hollow the object is, the greater the moment of inertia, if it has the same mass. All these objects we'll consider have the same mass. So I'm looking at these four. I'm looking at F, G, H, and I. So the object that has the greatest moment of inertia of these four is which one of these four? Which is the greatest quantity? 1/2 mr squared, mr squared, 2/5 mr squared, or 2/3 mr squared? Which is the greatest quantity?
The second one.
The mr squared. Mr squared. So 1 is bigger than 1/2. So that coefficient in front of the mr squared. So moment of inertia is always some quantity, some number, multiplied by mr squared. That number could be as great as 1, but often it's less than 1. So the greater the moment of inertia, then the less will be this velocity. Because the more moment of inertia the object has, you have a certain amount of potential energy at the top of the slope. The greater the moment of inertia, the less will be the velocity. We could also write this out as, what is the connection between omega and v? And we had v equals r omega. And so these are quantities that we derive. I don't want to go through the derivation again. We did this last time. So you could write that as 1/2 I omega squared would be v squared over r squared. So mgh. So therefore mgh equals 1/2 mv squared plus 1/2 I v squared over r squared. So it's the I that's going to be crucial in determining the difference between the final velocity. So the greater this I, the moment of inertia, then the less will be the velocity. You could rewrite the equation and maybe put I in a different place. V will be less if I is greater. So the object that has the greater moment of inertia will have the lower velocity, and hence will lose the race. So, going back to this. So anyway, let's see how it goes. I'm going to run that